Okay guys, hello, welcome to a video. I did a whole video on LRU Cache, but then I realized I was playing Ghibli music in the background and that's gonna get copyright striked. So, why don't we just try do it again, which is fine with me. So today we're gonna be doing an LRU Cache, and we're gonna be doing this in O1 lookup and O1 insertion and deletion. In order to do that, we'll be using a doubly linked list and a hash map to keep track of all our nodes within it. A use case for when we might use LRU cache is, let's say I have a very expensive function and I memorize this function so I can reduce the complexity cost, and I store this output of this function into a normal hash map. But then I realize this hash map only will grow in size, which is quite bad. It might cause to a memory leak. So I decided that I'm going to get rid of the least recently used units, which is perfect for this LRU cache scenario. So let's get right into the coding. LeetCode has provided us with some boilerplate code, but before that we do need some more. We need our own custom node definition. So initialization function for our node is going to be self, of course, because it is an object. Okay, so it's not quite true, but we do have self so that we are able to hold a reference to the node. Yep, so we do have a reference to the current instance of node. For this question, we will be having a key and a value, so our node instance will have, well, a key and a value as well. So self.key equals key, and self.value is going to equal value. Because it is going to be a doubly linked list, we're going to have a next pointer, which we will initialize to none, and doubly it's going to point backwards as well, which is done as well. So that's it for our node data class, which is nice and easy, our node class. Yeah. Let's get into our actual LRU cache. One of the most important parts of a cache is its capacity, because we do not want to store everything into a cache. So when we initialize our LRU cache, we actually define how big the cache might look like. Next, arguably most important thing is the cache itself. We'll be using a dictionary or a hash map for this, so we can do O of 1 average time complexity for the get input functions. How we actually use the doubly linked list is going to have two dummy functions, two dummy pointers, sorry. We're going to have two dummy nodes. So we're going to have a head node, just initialize it with none and none. And similarly, we're going to have a tail node. So how this works is that our tail is going to keep reference to the least recent. So the next value of the tail is going to be the LRU node. And there's going to be some values. And then our most recently used node is going to be on what's going to be the previous of our head. But when we do initialize it, we're going to just set the previous of the head as the tail and the next of our tail as the head. So that's it when we initialize our cache. And just before we get into the other two, we just need a bit more output functions. So insert, where we're going to insert the node. So when we insert into our linked list, we're always going to be inserting into the most recently used node over here. We can see that that's going to be right before the head. So whatever is used to be here will be bumped down here, and then our new node will replace the most recently used node. So first things first, we need to get the node that is the currently most recent used node. So head node, and then we said this is going to be one previous from our head. So head node's next is going to point towards our node, and our node's previous is going to point towards the head node. This is true as it is a doubly linked list. And then similar thing for our head. Our node next is going to point towards the head, where the head's previous is going to point towards our node. Since we did insert, it is just right to do delete as well. Similarly, it's going to take any node. If you think about how we're going to delete a node, think about three nodes in succession. This node points to the middle node, points to the next node. If you want to delete the node in the middle, we can simply, the previous node can simply skip the middle node and point to the one after. But first things first, we need to actually know what the previous node is. So previous node is literally the previous node, and the next node is literally the next node. Like I said before, the previous node is going to point towards our next node, and the next node's previous is going to point towards the previous node. Let's throw delete. Now we have one more function, which is the pop function. And the pop function is always going to delete this LRU node here. We will use this pop function when we try to insert into our cache, but it has reached capacity. So first we need to get the node to delete, and we said the node to delete is the one right after the tail. So self.tail.next, and then we can simply use this delete function that we have already. Self.delete, self.delete, and then we're going to be deleting the node. Then one more thing is we'll actually have to delete this from our cache as well. To delete.key. Cool. Now let's start off with our put function. So it says if the key exists, we'll update the value. How are we actually going to do this? If the key already exists in our cache, we're simply just going to remove it from our cache and our linked list as well. So first we're going to remove it from a linked list. We are expecting to pass in a node. So it's going to pass in the node. Then we said we're going to delete it from our cache as well. Key. Cool. And another requirement was that if the numbers of keys exceed the capacity, so if the number of, so if our cache is currently equal or greater than the capacity that we agreed on, capacity, we will be deleting, or we'll be popping from our delete linked list. Next, we can actually create the node in question. So this will be the key and value. And then we can insert this node into our doubly linked list, and we can create a dictionary mapping for this node. Now, something for our get. Now, first things first, we actually need to check if the key is inside our cache. If key is not in self.cache, we'll simply return -1, as they say here. But let's say it is. Then what do we have to do? We have to move that node to the very front. So first things first, we need to actually find out what the node is. Cool, now that we've got it, we can delete it from our W linked list. So self.delete. What are we deleting? The node, and then we can simply insert it back into the front of the node. And obviously we will have to return the node's actual value. So if we run this, oops. There we go. This has to be square brackets, accepted, and if we actually run it for our submission, yep, maybe the wrong function, should be delete, not remove, and then we can see that has been accepted. Cool. Thanks for watching, guys.